Hello friends, I welcome you in lecture number 10 on normal probability distribution. In this lecture we are going to discuss question asked in GTU Summer 2020 exam. So let's try to understand what is this question. It is given that a safety engineer feels that 30% of all industrial accidents in her plant are caused by failure of employees to follow instructions. If this figure is correct, find the probability that among 84 industrialized accidents in this plant, anywhere from 20 to 30 inclusive will be due to failure of employees to follow instructions. So here it is given that in some industrialized plant 30% of all accidents are caused by failure of employees to follow instructions, and they have given 84 industrialized accidents, and among these 84 industrialized accidents we have to find the probability that accidents between 20 to 30 will be due to failure of employees to follow instructions. So if we define our random variable capital X as, suppose we define capital X as number of industrial accidents in a plant, or we can simply write number of industrial accident caused by failure of employees to follow instructions. So here we can consider that for any industrial accident there are two possibilities: either it is caused by failure of employees to follow instructions, or it is not caused by failure of employees to follow instructions. And here they have given 84 industrialized accidents. So total number of accidents are given to be n equal to 84. So therefore possible values of random variable x are 0, 1, 2 up to 84. So out of these 84 accidents there might be 0 accidents which are caused by failure of employees to follow instructions. That might be only one accident which is caused by failure of employees to follow instructions, and so on. Maximum possibility is 84. Now suppose we define success as the event that industrial accident is caused by failure of employees to follow instructions. Failure of employees to follow instructions. That means an industrial accident occurs due to failure of employees to follow instructions. We define this event as success, and it is given that 30% of all industrial accidents in her plant are caused by failure of employees to follow instructions. That is, probability of this event, which is probability of success, is 30%, that is 0.3. So the probability of success is given to be p equal to 30%, that is 0.3. So this is the problem of binomial distribution. We can see here number of trials are nothing but number of accidents. They are finite. It is clear that they are independent. Also, if we consider any accident, there are two possibilities: that accident is caused by failure of employees to follow instructions, or it is not caused by failure of employees to follow instructions, and it is given that this probability is constant for every accident. So this is the problem of binomial probability distribution, and we are asked this probability that among 84 industrialized accidents we have to find this probability. Among 84 industrialized accidents in this plant, anywhere from 20 to 30 inclusive will be due to failure of employees to follow instructions. That means we have to find out probability of this event. Capital X lies in between 20 and 30, and we have to include 20 and 30. That is, number of accidents between 20 to 30 will be due to failure of employees to follow instructions. So we have to find out this probability. Now if we use binomial probability distribution to find out this event, then we can see we have to calculate probabilities starting from 20 up to probabilities that x equal to 30. So this will take so much time, it will require large number of calculations if we are using probability mass function of binomial distribution. And in another way we can write this as probability that x is less than or equal to 30 minus probability that x is less than or equal to 19, because x is a discrete random variable. So we have to calculate these probabilities. So cumulative binomial probability tables are not available for these values, so we cannot use tables also. So it is not advisable to use binomial probability distribution to find out this probability, because it will take so much of our time, because we have to calculate probabilities starting from x equal to 20 to x equal to 30. So as we have discussed in earlier lectures also, that if we are not comfortable in applying binomial probability distribution, then we can approximate binomial probability distribution using normal distribution if certain conditions or certain rules are satisfied. So we have discussed this condition, that if n into p is greater than 5 and n into 1 minus p is greater than 5, then we can approximate binomial distribution using normal distribution. So here we first check whether these two conditions are satisfied or not. So here n is 84 and p is 0.3. So first we write here that here capital X is a binomial random variable with n equal to 84 and probability of success p equal to 0.3, but we are not applying binomial distribution. So now we check that what is n into p and n into 1 minus p. N is 84 into 0.3, so if you calculate you will have 25.2, which is strictly greater than 5, and n into 1 minus p, that is 84 into 1 minus 0.3, that is 0.7, and this is approximately 58.8, which is also greater than 5. So therefore we can approximate binomial random variable, or we can approximate binomial distribution using normal distribution with mu equal to we know that mu equal to n into p, and n into p we have written here, it is 25.2. To use normal distribution we require mu, that is mean and standard deviation or variance, and variance is obtained by sigma square equal to np into 1 minus p. This n into p is 25.2 into 0.7, and that you will obtain as 17.64. so therefore standard deviation is square root of 17.64, which is nothing but 4.2. so we will use this mean mu equal to 25.2 and sigma equal to 4.2. so we will approximate binomial random variable by normal random variable with mu equal to 25.2 and sigma equal to 4.2. so we recall that whenever we are approximating discrete random variable or binomial random variable here by normal random variable, we will remember this continuity correction. If we have this type of probability that capital X is less than or equal to X, then this will be approximated by probability that capital X is less than or equal to X plus 0.5. Here X is normal random variable, here X is binomial random variable, and if we have this type of probability, then we will approximate it by subtracting 0.5. so with this in mind, we are able to solve our problem here. so now we check what is the required probability. so required probability is we have to find out that among 84 industrialized accidents in this plant, anywhere from 20 to 30 inclusive will be due to failure of employees to follow instructions. That is, this is the required probability. So we can write that probability that number of accidents caused by failure of employees, number of accidents caused by failure of employees to follow instructions, so this number is anywhere from 20 to 30, is anywhere from 20 to 30, and we have to include 20 to 30, 20 and 30 we have to include. so in the bracket we write that 20 to 30 inclusive. so this we can rewrite as random variable capital X lies between 20 and 30. Now here X is a binomial random variable and we are approximating it using normal random variable. so here on the right hand side I have this type of situation, capital X is less than or equal to X. so this I remember that if we have this type of probability, then we use continuity correction in this way, that is we add 0.5. so on the right hand side I will consider X is less than or equal to 30 plus 0.5. Similarly, we remember this, if capital X is greater than or equal to X, then we subtract 0.5 from X. So here we have 20 is less than or equal to X, that is we have this type of situation, 20 is less than or equal to X. so this we will write as 20 minus 0.5 is less than or equal to X. so here I consider 20 minus 0.5 less than or equal to X. so I am adding 0.5 on in 30 and I am subtracting 0.5 from 20. Okay, and we can write this also if we wish. It is not necessary to write this. So this turns out to be probability that 19.5 is less than or equal to X, and this is less than or equal to 30.5. Okay, this is just for understanding. So now here x is a non-standard random variable, so we standardize it by considering x minus mu over sigma. So here we consider 19.5 minus mu over sigma, which is less than or equal to x minus mu over sigma, and less than or equal to 30.5 minus mu over sigma. And we have obtained values of mu and sigma that we substitute here. 19.5 minus what is mu and sigma. Mu is 25.2 and sigma is 4.2. So 19.5 minus 25.2 divided by 4.2, and this is x minus mu over sigma is standard normal random variable, and here we have 30.5 minus 25.2 divided by 4.2. So if we simplify this, I have my calculations that I am writing. Probability that minus 1.36 is less than or equal to capital Z, which is less than or equal to 1.26. Now using the property of distribution function, this we can rewrite as probability that Z is less than or equal to 1.26 minus probability that Z is less than or equal to minus 1.36. Now to obtain these two probabilities, we will use cumulative normal probability table for standard normal random variable. So first we find out probability that Z is less than or equal to 1.26. So here I have this standard normal curve areas. I have probabilities of this type. Capital Z is less than or equal to small z. I am interested in this probability less than or equal to 1.26. So for that I consider 1.26 as 1 plus 1.2 plus 0.06. So I have to look for 1.2 under these values of Z, and 0.06 is here. So I will take intersection of 1.2 and 0.06. First I will search for 1.2 below this Z column. So 1.2 is here. Okay, so we have 1.2 here and 0.06 is here. So if we take intersection of these two, I go up to this, and from here I go up to this. So I have at the intersection point I have this value 0.8962. Okay, so probability that Z is less than or equal to 1.6 is nothing but 0.8962, that we write here 0.8962. Now we calculate this probability. Capital Z is less than or equal to minus 1.36. So again we come here, we have to search for minus 1.36. That means this I can rewrite as minus 1.3 minus 0.06. So here also I have to concentrate on minus 1.3 and 0.06. So first I consider minus 1.3. So minus 1.3 is here and 0.06 is here. So I can count from 0 up to 6. So minus 1.3, this is for 0, this is 0.01, 0.02, 0.03, 0.04, 0.05, and this is 0.06. Okay, we can count in this way: 0, 1, 2, 3, 4, 5 and 6, and we can observe that this is the column corresponding to 0.06. Okay, here we have 0.06. So at the point of intersection we have 0.0869. So this probability is 0.0869, and if we take the difference we have 0.8093. So this is the required probability. If we round off up to 2 decimal places, we have 9 here. So this is 0.81 approximately. So 0.81 is the probability that number of accidents will be in between 20 and 30. 20 less than or equal to x less than or equal to 30 is approximately equal to 0.81. So this is also the problem of binomial distribution, which we have approximated by using normal random variable, and this is very easy. We just have to remember that if n into p is greater than 5 and n into 1 minus p is greater than 5, then normal distribution is good approximation for binomial distribution. And we have to remember that continuity corrections while using binomial random variable to approximate normal random variable. So if we have this type of probability, capital X is less than or equal to x, we have to add 0.5 to x. If we have this type of probability, we have to subtract 0.5 from x. Okay, so with this in mind, we can easily apply normal approximation to find out binomial probabilities. So this is all about this session. I hope you like it. Thank you very much.